So you should now be starting part 2. It's just the second video in the series. I really wanted to pause for a moment when we got to this image because I want to dig deep into it and I didn't want it to get lost in the video. So if you came back to it, you were like, gosh, I really want to go right back to where she talked about that Newton's cradle picture, you can just start part 2 and you're right here, okay? So when we look at this picture, we can see we have ball A, which is moving here. So it looks like 3 balls, but this is really all the same. Ball A, B, C, D, and then ball E is right here. It looks like it's 3 balls, but it's really all the same. So we have 1, 2, 3, 4, 5 balls in this Newton's cradle that we're working with. Okay, I want to clarify, you've got 5 balls in this Newton's cradle that we're working with. Sorry, I just decided to hide my tools to get them out of the way. So if a person were to take ball A and move ball A out to the left, this would be my left. If they take ball A and move it out to the left, the gravitational energy, the GE, the potential energy to move is at its maximum. It has 0 kinetic energy and it has 0 speed because it's not moving. But as it transfers from this pulled out spot toward the cradle, as we're following this green arrow as it's coming back to the cradle, ball A is gaining kinetic energy because it's moving and it's losing its gravitational energy. We're going to ignore this red part for right now. So right here at the starting point, if I were to pull this ball out to start my Newton's cradle, ball A, I would have a maximum amount of gravitational energy, 0 kinetic energy, nothing's moving, and 0 speed. As it works its way back to the cradle following the green arrow, sorry, my dog just sneezed if you heard that in the background, it's gaining its kinetic and its movement energy. It's losing its gravitational energy. Let's talk about ball B, C, D, these balls here in the middle. They all have 0 gravitational energy. They're not being pulled out, they're not being pulled back, they're just completely at rest. They have 0 kinetic energy. They're not moving at all, and they have 0 speed. But as this ball A comes into the Newton's cradle and pushes across, you'll notice ball E, as we follow our red arrow up to the top, it's gaining gravitational energy. It starts off moving pretty quick. It starts off moving pretty fast. It's got that kinetic energy, but as it goes up to the top, it's gaining its gravitational energy, its potential energy. It's losing, it's slowing down, it's losing its kinetic energy. And when it gets to the very end of the motion, at the end of the cradle, it has its maximum amount of gravitational energy. It's not going to be moving at that top part, so it has 0 kinetic energy and 0 speed. These bullets are going to break down exactly what I just explained, but it's going to do it in the words of like an iQuest or a textbook. So when you pull ball A, it gets higher and gains gravitational energy. This energy is transferred to it from your hand. When you release ball A, it loses gravitational energy as it falls, but it gains kinetic energy. Its gravitational energy is transformed into kinetic energy. When ball A hits ball B, the kinetic energy of ball A is transformed into elastic energy because the ball gets compressed. The amount of compression is very small because the ball is made of steel, but it is still there. The elastic energy is transferred from ball A to ball B, which gets compressed. The elastic energy is transferred from ball B to ball C, and so on, all the way up to ball E. Ball E's elastic energy is transformed into kinetic energy, and in response, it starts moving sideways and upward. At this point, the energy ball A had at the start has been transferred to ball E. A very small amount has been transferred to the surrounding air as sound energy, and another small amount has been transformed into thermal energy. But just focusing on the gravitational, elastic, kinetic energy transfer and transformation is helpful right now. So if you go back to that first question, it asked what kind of energy has been moved into its surroundings. That's answered right here. A very small amount has been transferred into the surrounding air as sound energy. You can kind of hear them clinking on one another. That's that sound energy. And another small amount has been transformed into thermal energy. Those balls are going to gain a little bit of heat as they touch. That's that thermal energy. So Back to the reading. This is why ball E moves away from the other balls at the same speed that ball A hit ball B. While moving upward, ball E's kinetic energy is transformed back into gravitational energy. Once all its kinetic energy has transformed into gravitational energy, ball E stops rising. It is now at its highest point, which is the same height at which ball A was released. This process repeats itself in reverse when ball E swings back toward the other balls. Thus, Newton's cradle involves 4 types of energy transformation. Type 1. Gravitational energy transfers to kinetic energy. Kinetic energy to gravitational energy. Kinetic energy to elastic energy. Elastic energy to kinetic energy. In addition, the cradle involves the transfer of elastic energy between different balls. Although the amount of energy each ball has changes during these energy transfers, the total amount of energy possessed by the cradle as a whole, if you ignore the little bits of energy transferred to the surrounding air, does not change. It is just transferred from one component of the system to another component. If you visited a virtual Newton's Cradle website or played with the real device, you might have noticed that after a few swings, the ball slows down. The height they reach gets shorter and shorter until they finally stop moving. So question number 2. If energy is transformed from one type to another type and is transferred between the different balls in the device, why does the motion in Newton's cradle finally stop? Hint. Think about something you decided to ignore earlier in the reading. So remember that part that I highlighted earlier? That's my big hint for you. What's happening as this energy is transferring? If energy is transferring, technically, shouldn't the Newton's cradle go on forever? It doesn't go on forever. But why do you think it finally stops? Where is some of that energy going each time that the Newton's cradle goes? This is a tricky question. Go back to what I highlighted in the previous paragraph. That's really going to be my key hint for you here. If you'd like, you can pause right now, answer the question, or you can continue on with me as I wrap up our summary. By now, you understand some things about how Newton's cradle works. You can explain why the speed and the height of the balls are equal in both sides of the device, but you may not be able to explain why the balls in the center do not move or why the same number of balls move on both sides. In order to understand this phenomenon, you need to learn more about forces in motion. As you continue investigating motion during this unit, you will learn how and why things move the way they do. So hopefully you guys are able to answer these questions to the best of your ability. Please remember to answer in a color other than black. Red is fabulous. Always, always, always answering complete sentences. And just to reiterate, that video 1 takes you right up to that really big image with kind of the confusing words. It's just a crazy model. This part 2 video starts right at that model. So if you want to reference back to it, you can just start that video, that part 2 video, and you'll be right there at that model. You don't have to be scrolling through a longer video to find it. Please submit this on Google Classroom, you guys. Have a great rest of your day.